Well, in this video, we're going to begin examining the law of conservation of energy and energy transfers and transformations. To begin, we need to develop a basic model of energy. Energy can be a fairly elusive concept, so to begin, we're going to look at an analogy of an energy model. So before continuing, at this point, pause the video and read it's called The Parable of the Lost Penny in your reading packet or on page 296 and 297 of your textbook. So pause the video and read that before continuing. So one of the greatest and most significant discoveries of science is that there is a natural money, like in the story, that we call energy. So there's a wide variety of different types of energy, such as kinetic energy and gravitational potential, elastic or spring potential energy, thermal energy, chemical energy, nuclear energy, all these different types of energy. And one of the things that we're going to be primarily concerned with is energy transfers and transformations, and applying those transfers and transformations to the concept of energy conservation. Like the law of conservation of momentum, the law of conservation of energy states that in a closed system, energy is conserved. Now, surprisingly, the law of conservation of energy was not recognized until about the mid-19th century, long after Newton. The reason was similar to John's lost penny, was that it took scientists a long time to realize how many types of energy there are and the various ways that energy can be converted from one form to another. And as we'll soon learn, energy ideas go well beyond Newtonian mechanics to include new concepts about heat, about chemical energy, and about the energy of individual atoms and molecules that comprise an object. All of those forms of energy will ultimately have to be included into our little accounting scheme for energy. But those are in future units. For now, our basic energy model is that we will be the energy that goes into a system has to equal the energy that comes out of the system. There can be a wide variety of types of energy within the system, and these can be transformed back and forth without any loss, but the overall amount of energy in a system remains constant. Now, when we start talking about a system in relation to problem solving in energy conservation, what we're really talking about is called a closed system. That is, it's one where the energy of the object or objects we're looking at is isolated from the environment. And when we use a closed system, we can explore any energy input into the system and any energy output without worrying about how that energy changes within the system. Or we can look specifically at the energy changes within the system without having to worry about where that energy is coming from or where it's going to. So we'll talk about more about isolated systems or closed systems here coming up in just a moment. But first, a system may have many different kinds of energy present at once. For example, a moving car has kinetic energy of motion. It has chemical energy stored in the gasoline, thermal energy in its engine, and any other forms of energy in its many, many other parts. However, the total energy of the system is just the sum of the different energies present in that system. So the energies shown in this sum are the forms of energy in which we'll be most interested in at this point. These dots represent just continued other types of energy that could be there, such as nuclear or electric, that might be present in that system. So one of the most remarkable things about energy is that one type of energy can transform into another type of energy. The gravitational potential energy of a roller coaster at the top of a track is rapidly converted into kinetic energy as the coaster descends. Or the chemical energy of gasoline is converted into the kinetic energy of a moving car. Now this table here illustrates a few common energy transformations, and in it, here we've got an arrow used as a shorthand way of representing an energy transformation. What's common about each of these energy transformations is that they all occur within the system being looked at. That is, energy transformations are changes of energy within the system from one form to another. And another amazing thing about energy is not only can it be changed from one type to another, it can be transferred from one object to another. So in our monetary model, energy transformations are like John's shifting of money between his own various assets, such as from his savings account to stocks. But John also interacted with the greater world around him, receiving money as income and outlaying it as expenditures. Every physical system also interacts with the world around it, that is, with its environment. Now, in the course of these interactions, the system can exchange energy with the environment. And an exchange of energy between a system and its environment is called an energy transfer. There are two types of energy transfer processes, two primary types. The first energy transfer process is called work. Work is the mechanical transfer of energy to or from a system by pushing or pulling on it. So work is a mechanical transfer of energy due to forces being exerted. And then there's heat, which is the non-mechanical transfer of energy from the environment to the system because of a temperature difference between the two. In this unit, right now, we're just concerned ourselves with work, and we'll save heat for our unit on thermodynamics. So in physics, we define work a little differently than what's used in the common language. In physics, we define work as the process of transferring energy from the environment to a system, or from a system to the environment by the application of mechanical forces, so pushes and pulls to that system. Once the energy has been transferred to the system, it can appear in many forms. Exactly what form it takes depends on the details of the system and how the forces are applied. Now, this table here gives a few examples of energy transfers due to work. We use a W as a symbol for work. Notice that in each of these examples, the environment applies a force while the system undergoes a displacement. Energy is transferred only as work, only when the system moves while the force acts. A force applied to a stationary object, such as if you were to push against a wall or push a car and it doesn't move, transfers no energy in those cases to the object and does no work. So it's also possible to convert work into, say, gravitational potential energy or electric potential energy or even chemical energy. We'll have a lot more to say about work in the next lesson, but the key points to remember right now about work is that it's a transfer of energy from into a system or out of a system by the application of forces, and the system must be displaced in order for that energy to be transferred. Now, the law of conservation of energy simply states that in a closed system, energy is conserved. That energy can be transferred, it can be transformed, but the overall amount of energy in a system remains constant. One way to illustrate this is with this relationship shown here, that all of the forms of energy that could be in a system, it doesn't mean that all of these always are in a system, but that energy is going to remain constant. Okay. Another way to think of this is conservation law is in terms of energy changes. So if an isolated system has a change in its kinetic energy by delta K, say, its gravitational potential energy by delta U, and so on, then the sum of these changes is the change in the total energy. But since the total energy is constant, its change is zero. So we can rewrite the law of conservation of energy in this form here, where we're dealing with the changes of energy. Okay? This is kinetic energy. This is gravitational potential energy. This is what's called spring potential energy. This is thermal energy, and this is chemical energy. And again, these aren't always involved in every system that we look at. They're just examples of what could be there. Now, any increase in energy from one form to another must be accompanied by a decrease of energy in other forms, so that the total change is zero. For example, this fellow here is pushing on a box. His chemical energy decreases as he pushes on that box. That energy gets transferred into that box, and the kinetic energy of the box increases. So his chemical energy goes down as the kinetic energy of the box increases. And if he's on like a concrete floor, we've got friction involved. We've also got some thermal energy that's going to be released into the environment. So what this is showing us is that the law of conservation of energy sets a constraint on those processes that can occur in nature. Any process that occurs within an isolated system, that changes in each form of energy has to add up to zero. Now, to apply the law of conservation of energy, we'll need to carefully define which objects make up the system and which belong to the environment. The choice will affect how we analyze various energy transfers and transformations that occur. In doing so, we need to make a distinction between two classes of forces. Internal forces are forces between objects within the system. So if a weightlifter and barbell are both part of the system, the forces of the weightlifter on the barbell and the barbell on the weightlifter are both internal forces. Internal forces are responsible for energy transformations within the system. Because they're internal to the system, however, internal forces cannot do work on the system and thereby change its energy. External forces act on the system, but their agent is part of the environment, so they're outside the system going into that system. External forces can do work on the system by transferring energy into or out of it. Whether a given force is an internal or external force depends on the choice of what's included in the system. And we're going to talk more about energy transfers and transformations and how to make sense of them in the next video. And then after that, in the fourth video, we'll talk a little bit more about work, and then we're going to get to a point where we can start putting some quantitative thinking into these energy transfers and transformations and conservation of energy and work, and eventually get to what's called power. All right, well, we'll see you in class.